Today we're going to have a quick tutorial on operations involving complex numbers. Now the basic thing that we need to remember about complex numbers is that, as we know, square root of negative number will always be undefined or does not exist because the square root of a negative number by definition does not exist. Now mathematicians were able to come up with ways on how to represent the square root of a negative number by introducing the value of an I. So every time we see a square root of a negative number, we always associate it with the complex number I. So every time we see a square root of negative 1, we can change it into I or replace it with the imaginary number I. Now we have three examples here wherein we have square root of negative numbers. So for problem number 1, we have square root of negative 2. Now by the property of the square roots, we know that we can factor out negative 2 by negative 1 and 2, leaving us with square root of negative 1 and square root of negative 2. And by doing so, we are seeing now that square root of negative 1 can be replaced by an I, and the square root of 2 will just be square root of 2 because it's not a perfect square. So the simplest form or the modified form of square root of negative 2 will be I square root of 2. And this particular example is true to any prime numbers that's inside the square root and negative. For example, if we have square root of negative 3, it will be I square root of 3, or square root of negative 5 will have I square root of 5. All of which are prime numbers. That is why we can rewrite it into this particular form, similar to problem number 1. Now we also have numbers that are perfect squares, like the example number 2. We have square root of negative 81, which when we factor out the negative 1, we'll have square root of negative 1, which we know is an I, and square root of 81, which is a perfect square, will give us 9. So we'll have I9, or as we write it in complex number, 9 and then the imaginary number I. So every time we have a perfect square and it's inside the square root and it happens to be a negative number, all we have to do is to add I in our square, or in our simplest form of the square root of a negative number. For example, square root of negative 4 is 2I, square root of negative 36 is 6I, and square root of negative 64 would be 8I, because all of those numbers that I've mentioned are all perfect square. Now the last example, we have square root of negative 12. Now this one is a special case because we know 12 can have or can produce a factor that is a perfect square. So the factors of 12 could be 4 and 3, and we know that 4 is a perfect square. So when this happens, we can simplify the radical or the square root of positive 12 into 2 square root of 3, because the square root of 4 is 2. So the final answer, or the simplest form of square root of negative 12, will be 2I square root of 3. So these three examples of complex numbers or imaginary numbers are pretty similar to some of the numbers that you will encounter with complex numbers. So this is the imaginary number, and this is a huge part in understanding what complex numbers are. Now by definition, complex numbers are basically numbers with real part and imaginary part, wherein A and B are both real numbers and the imaginary number is going to be related to B. So example of complex numbers are 7 plus 5i, wherein the real part is 7 and the imaginary part is 5i. And we also have 2 minus square root of negative 9, that, as we know, the square root of negative 9 will simply equal to 3i, so we'll have a real part of 2 and imaginary part of 3i. So we have 2 minus 3i from 2 minus square root of negative 9. And if we have 3i plus 6, notice that the imaginary part came first before the real part, and to write it in standard form, we always have to write the real part first and then the imaginary part. So we'll have 6 plus 3i. So these are some of the examples of the complex numbers that we're going to deal with in this lesson, because for today we're going to be working on operations involving complex numbers. So let's start with adding and subtracting complex numbers. Now in adding and subtracting complex numbers, we simply associated with combining like terms or addition and subtraction of polynomials. So in this particular case, we have real part and imaginary part. So if you're going to look at problem number 1, we have 8 plus 6i plus 3 plus 2i, the real part, which is 8 and 3, and the imaginary part, which is 6 and 2, can be combined, giving us 8 plus 3 and 6 plus 2, with, of course, the imaginary number I. And by simplifying the expression, we'll have 11 plus 8i. So this is how simple addition of complex numbers are. You just need to find the real part and the imaginary part and then combine the like terms. So in problem number 2, we have subtraction of, or getting the difference of 3 plus 2i and 5 minus 2i. So we're simply subtracting 3 minus 5 and 2i minus negative 2i, giving us negative 2 plus 4i, because 2 minus negative 2 will turn into a positive. That's why we have 4i as a result. So this is how we add and subtract complex numbers by combining the real part and the imaginary part. Now in this particular example, problem number 3, we need to produce the imaginary part in this expression by simplifying the square root of negative 64 and the square root of negative 4, which happens to be perfect squares. So negative or square root of negative 64 and square root of negative 4 can be modified into 8i and 2i respectively. So we'll have 8 plus 8i minus 5 minus 2i. And by combining like terms, we'll have 8 minus 5 and 8 minus negative 2i, giving us 8 minus 5 plus 8 minus 2, or 8 plus 2i, which is 3 plus 10i. So this is how we simplify complex number by addition and subtraction. And now we're going to multiply complex numbers of the form a plus di and a plus di. Now before we multiply complex numbers, we need to remember the properties about I squared, or the definition of I squared, which is equal to negative 1. And if we're going to apply the rules of algebra in evaluating why I squared is equal to negative 1, we know that I is equal to the square root of negative 1. So if we're going to have an I squared, we're going to square root of negative 1, which we know square root or square can undo the square root. So if we cancel out the square root and the square, I squared will give us negative 1. So just remember that every time you are seeing I squared in an expression, just replace your I squared by negative 1 and simplify your expression. So let's use our I squared in some of the expressions that we're going to have in our example. So for problem number 1, we have 2i squared. And we know that even though I is an imaginary number, by simplifying I squared by changing it into negative 1, we'll have negative 2 as a result. So in this particular case, from an imaginary number 2i squared, we're able to transform it into a real number, which is negative 2. So the idea of I squared is that it turns an imaginary number into a real number. So if I have 5 minus 7i squared, I know that I squared is negative 1. So all I have to do is to eliminate I and switch my sign from negative to positive. So that's how I look at an I squared. I squared simply drops the I and then switch the sign of my real number from positive to negative, or if it's a negative, it will become a positive. So if I have 5 minus 7i squared, it will simply give me 5 plus 7, which is equal to 12. So that is how we evaluate or use I squared in a complex number. Now, how does I squared be used to multiplying complex numbers? Say we have square root of negative a times square root of negative b. The product of square root of negative a and square root of negative b by the formula is equal to negative square root of ab. So for example, if we have two numbers two numbers which are both negative and are both inside the square root, we'll use this formula to evaluate it. So let's have a numerical example of this property of complex numbers. Let's say we have square root of negative 2 times square root of negative 5. To be able to simplify the expression, all we have to do is to separate the I for square root of negative 2 and the I for square root of negative 5, giving us I squared of 2 and I squared of 5. And by multiplying I times I and multiplying square root of 2 and square root of 5, we'll be able to produce I squared times square root of 2 times 5, which gives us negative square root of 10. So this is how we evaluate square root or expressions similar to square root of negative a times square root of negative b, because a common mistake that most students will do is to simply multiply square root of negative 2 times square root of negative 5, which will give them square root of positive 2 times 5, which is not a correct algebraic rule in simplifying square root of a negative number. So for problem number 2, we have square root of negative 49 times square root of negative 25. We know that 49 and 25 are both perfect squares. So the square root of 49 is equal to 7 and the square root of 25 is equal to 5, leaving us with an I squared, which will turn into a negative 1. So 7 times 5 is equal to 35, giving us negative 35. So square root of negative 49 times square root of negative 25 is simply negative 35. And if I have 2i times 5i, 2 times 5 is 10, and I times I is equal to I squared. So I'll have 10i squared, which will give me negative 10 as a result. Now, using the distributive property for complex number is also possible, since we have a real part and an imaginary part. Say, for example, we are multiplying negative 4i, which is an imaginary number, to 3 minus 5i. By the distributive property, we'll be able to multiply negative 4i to 3 and negative 4i to 5i. So leaving us with negative 4i times 3, which is equal to negative 12i, and negative 4i times 5i, which will leave us with negative 20i squared. So in our expression, we know that I squared will turn into a negative 1. So it will give us a negative number for negative 20, and double negatives become positive. So we'll have negative 12i minus 20. So this will be the product of negative 4i and 3 minus 5i. Negative 20 minus 12i. And for problem number 2, we have 1 plus 2i times 1 plus 3i, which is similar to the product of two binomials. And when we're dealing with the product or multiplying two binomials, we know that we are using the FOIL method. First, outer, inner, last. So in this case, we'll multiply 1 times 1 and 1 times 3i, and then we multiply 2i times 1 and 2i times 3i, giving us 6i squared. So you will notice that the middle terms will be 3i and 2i, which basically are both like terms. And we also have an I squared as our last term, and we know that an I squared will turn into a negative 1. So we'll end up with 3i plus 2i, which is 5i, and 6 times negative 1 will turn into a negative 6. So we'll have 1 plus 5i minus 6. And by combining like terms, 1 minus 6 is equal to negative 5. So our final answer will be negative 5 plus 5i. So in multiplying complex numbers, it is quite similar to multiplying polynomials using the FOIL method and the distributive property. Now for problem number 3, we have 1 minus 2i quantity square. So by expanding our complex number, we'll be able to produce 1 minus 2i times 1 minus 2i. So by using the FOIL method, we'll be able to produce 1 minus 2i minus 2i plus 4i squared. And by combining the middle term and simplifying I squared into negative 1, we'll end up with 1 plus 4i minus 4. And 1 minus 4 is equal to negative 3. So the product of 1 minus 2i times 1 minus 2i is equal to negative 3 plus 4i. Or also, if you want to put it as 1 minus 2i quantity squared, it's equal to negative 3 plus 4i. And for the fourth example, we have 3 minus 4i times 3 plus 4i. Now, using the FOIL method, we'll be able to produce 9 plus 12i minus 12i minus 16i squared. Now, notice that the middle terms, which is 12i minus 12i, will turn into a 0, and I squared will turn into a negative 1. And when this happens, we'll end up with 9 minus negative 16, and we know that 9 minus 16 is 9 plus 16, so we'll end up with a real number, which is 25. So this particular phenomenon is what we call as multiplying a complex number by its conjugate. And if that happens, the imaginary part of our complex numbers will disappear or will be eliminated. So this particular case is a special case in complex numbers because 3 minus 4i and 3 plus 4i are what we call as the complex conjugates of our complex numbers. So if we have a complex number, say a plus bi as its general form, the complex conjugate of a plus bi will be a minus bi. So if we have a minus bi, its complex conjugates will be a plus bi. And if we are multiplying complex conjugates of complex numbers, we are simply multiplying or taking the squares of the first term or the real part and taking the squares of the imaginary part and then adding them up. So 3 times 3 and 4 times 4 is going to be our imaginary part and the real part, and by simplifying it, it will give us 9 plus negative 16i squared, and we know that I squared is equal to negative 1, and we'll end up with 9 plus 16, which is 25. So using a formula for conjugates or complex conjugates, always remember that if you are multiplying a minus bi times a plus bi, it will equal to a squared plus b squared. This will save you a lot of time when you are multiplying complex numbers, and the complex numbers you're dealing with are considered to be the complex conjugates. So if we have 4 minus I times 4 plus I, we can quickly multiply them because the square of 4 is 16 and the square of 1 is 1, and 16 plus 1 is equal to 17. And if we have complex conjugates as 2 minus 5i and 2 plus 5i, 2 squared is equal to 4 and 5 squared is equal to 25, so 4 plus 25 is equal to 29. So this property of complex number is really useful when we are working with complex conjugates or rationalizing complex numbers, also known as division of complex numbers. So the last operation that we're going to be dealing with today will be division of complex numbers or rationalizing complex numbers. Now for a first example, we have 7 plus 4i divided by 2 minus 5i. And to be able to get rid of the complex number in our denominator, we're going to multiply the fraction, which is the numerator and the denominator, by the complex conjugate of the denominator. We also call this as rationalizing. So since the denominator is 2 minus 5i, its complex conjugate would be 2 plus 5i. So if we multiply the numerator and the denominator by the conjugate of the denominator, we'll be able to get rid of the imaginary number in our denominator. So let's simplify our product. So since we're multiplying the numerator, which is 7 plus 4i times 2 plus 5i, all over the complex conjugate of the denominator, we are going to be using the FOIL method for the numerator, and we're going to use the formula in simplifying complex conjugates, which is simply the square of the real part and the square of the imaginary part. So the numerator will take a little while to finish, but the denominator will be solved really quickly because of the formula. So by the FOIL method, 7 times 2 is equal to 14, 7 times 5 is equal to 35i, 4i times 2 is equal to 8i, and 4i times 5i is equal to 20i squared. And for the denominator, we're only squaring the real part, which is 2 squared, and the imaginary part, which is 5 squared, leaving us with 2 squared plus 5 squared. And by simplifying our numerator and the denominator, we'll have 14 plus 43i minus 20 all over 4 plus 25. And by combining like terms, we'll end up with negative 6 plus 43i all over 29. Now, to simplify our answer in standard form, we're going to separate the real part and the imaginary part, leaving us with negative 6 all over 29 plus 43 all over 29i. So this is how we write fractions in standard form. Now, notice that when we are simplifying, the numerator is always, or when we are rationalizing this type of fraction, the numerator is always a little bit longer to work with as opposed to the denominator. Now let's have a few more examples on how we rationalize or divide complex numbers. Now for problem number 2 and for problem number 3, notice that the denominators are different. For problem number 2, we only have the imaginary part, and for problem number 3, we have a complete set of a complex number. Now, rationalizing or dividing a complex number similar to number 2 will be a lot simpler than problem number 3. So to be able to rationalize or divide 3 all over 2i, all we have to do is to multiply the numerator and the denominator by I. So we don't need to consider the complex conjugate of the denominator anymore. So every time we are dividing by an imaginary number without the real part, we are simply multiplying the numerator and the denominator by an I. And by doing so, 3i or 3 times I is 3i, and 2i times I is equal to 2i squared. So notice that we have an I squared in our denominator, which will then turn into a negative 1. So we'll end up with 3i all over negative 2, leaving us a real number in our denominator. So to simplify 3i all over negative 2, we can rewrite this as negative 3i all over 2. And then we are able to rationalize again because the denominator doesn't have an imaginary part anymore. Now for problem number 3, we're not going to use the same technique for problem number 3 compared to number 2, because now we have a complete set of a complex number with a real part and imaginary part. So just like what we did in example number 1, we're going to multiply the numerator and the denominator by the complex conjugate. So notice that the numerator is now easier to simplify because we're not going to FOIL anymore but use the distributive property. So 3i times 4 will turn into a 12i, and 3i minus I will turn into 3i squared. And the denominator is the complex conjugate, so we'll just square the real part and the imaginary part to simplify the denominator. So we'll end up with 12i minus 3i squared all over 4 squared plus 1 squared. And by simplifying our I squared into negative 1, we'll end up with 3 plus 12i all over 17. And now we'll change it into the standard form wherein we have the real part and imaginary part. So we'll have 3 all over 17 plus 12 all over 17i. And since both fractions cannot be simplified anymore, this will be our final answer. And for the last example for rationalizing or dividing complex numbers, by multiplying the complex conjugate, we'll be FOILing the numerator and using the conjugate or complex conjugate formula for the denominator. So we'll end up with 10 plus 10i plus 6i plus 6i squared in your numerator, and we'll have the square of 2 plus the square of 2 in the denominator because they're complex conjugates. So by simplifying the numerator, we'll have 10 plus 16i minus 6, and 10 minus 6 is equal to 4. We'll end up with 4 over 8 plus 16i all over 8. Now, notice that our answer can still be simplified by simplifying our fraction. So 4 over 8 can be simplified into 1/2, and 16 all over 8 can be simplified into 2, leaving us with 1/2 plus 2i. And this is our lesson on operations involving complex numbers from addition up until division of complex numbers.